Okay, this is a continue of the last video, and we're going to look at some more of the specifics of the Diels Alder reactions. Okay, in the last video we talked about some of the considerations for the dienophile, and specifically that the reaction is more efficient when we add an electron withdrawing group to the dienophile. Here we want to consider some of the considerations for the diene. And so we learned in our video on the dienes that it can exist in either the S-cis or S-trans conformations. Well, the Diels Alder reactions can only occur when the diene is in the S-cis conformation. And one consequence of that, if a diene is trapped in the S-trans conformation, it can't undergo a Diels Alder reaction. So in this reaction, we have a diene, we have a dienophile with a good electron withdrawing group, but because of the cyclic nature of this molecule, it's trapped in the S-trans configuration or conformation, and so it can't undergo the Diels Alder reaction. On the other hand, if we have a diene that's locked into the S-cis conformation, it readily undergoes the Diels Alder reaction. So here we have cyclopentadiene, right? It can only adopt an S-cis conformation, and so this reaction is very efficient. It's very fast. But because we already have one ring, and the Diels Alder reaction is making a second ring, right? We get this bicyclic product when we have a cyclic diene. So normally the Diels Alder makes a cyclic hexene, right? And that's this one here, 1, 2, 3, 4, 5, 6. And then our original cyclic compound from the cyclopentadiene is the 1, 2, 3, 4, 5. Now, in fact, it turns out that cyclopentadiene is so reactive towards the Diels Alder reaction that it can actually react itself at room temperature to form this dimer, right? And this is a fairly complicated looking structure, but and it's sort of a tricyclic compound, but that makes sense. Both the diene and the dienophile have rings. The Diels Alder reaction makes another ring, and so that's why we get this tricyclic compound. It turns out that in order to use cyclopentadiene as a reagent, because this compound so readily forms at room temperature, we have to heat it up to get the retro Diels Alder reaction to happen, and then once we reformed the cyclopentadiene, then we can use it in the Diels Alder reaction. So when we start with a cyclic diene, and therefore end up with a bicyclic product, we use the terms endo and exo to refer to the positioning of these functional groups. Now, endo and exo has nothing to do with endothermic and exothermic. We're just using the same terms with different meanings in this case. So what these terms mean, when we have the bicyclic system that doesn't include the functional groups we're talking about, we have a smaller bridge and a larger bridge, right? This bridge is 1 atom, right? This bridge is 2 atoms. So the endo and exo refer to the positioning of the functional groups relative to the larger bridge. So when they're syn to one another, so the bridge is down and the functional group is down, that's endo. When the big bridge is down and the functional group is up, that's exo. It's anti to the larger bridge. So endo, the functional group is down as well as the larger bridge. Exo, the functional group and the larger bridge are pointing in opposite directions. Okay, so we can get both the endo and the exo positioning of the electron withdrawing groups. Which one is preferred? Well, the endo is greatly preferred over the exo position. And oftentimes, we only get the endo product and we don't see any of the exo product. In this example, the 2 electron withdrawing groups are cis, so they need to end up on the same side. And so we tend to prefer where both electron withdrawing groups are on the same side and they're both endo, as opposed to both of them being exo. Right? And because this was cis, they both have to be on the same side. If this had been trans, we would have gotten one endo and the other one exo, in which case it wouldn't have really mattered. All right, so this slide is an attempt to explain the preference for the endo position. The way the explanation goes, when they're in the endo position, we can get a favorable interaction between the pi electrons of the electron withdrawing groups and the pi electrons from the diene. When we form the exo position, the pi electrons and electron withdrawing groups are two away from the pi electrons in the diene, and so we don't get this favorable interaction. Now, I realize this explanation is a little bit unsatisfying. In order to really see what's going on, we have to look at the molecular orbitals of both the diene and the dienophile, along with the electron withdrawing groups. Those pictures can get a little bit complicated, and so I decided to omit them. If you're looking for more of an explanation, this is very similar to hyperconjugation that we talked about last semester. If you'd like to see some of these pictures and look at them with me, come see me after class or schedule time out of class, and we can talk about this more. So one thing that I thought was interesting to point out, because it relates back to something that we've talked about earlier in this chapter, the reason we see the endo preference is because that transition state sees the stability between the interaction between the pi electrons in the electron withdrawing group and the pi electrons in the diene. That stabilizes the transition state, lowering its energy, making the formation of the endo product faster. It turns out the exo product is actually lower in energy. It's actually more stable. So this is another example of kinetic versus thermodynamic control. It just turns out that kinetic control appears to be more important for these cyclic Diels Alder reactions. Okay, the next thing I want to talk about is the regiochemistry of the Diels Alder reaction. So what we're thinking about is, where do the electron withdrawing groups end up relative to any groups that happen to be on the diene? Well, it turns out if either the diene, or in this case the dienophile, is symmetric, it doesn't matter. There's only one regiochemical outcome. On the other hand, if both the diene and the dienophile are unsymmetrical, then we can have multiple possible regioisomeric products. Now, one of the regioisomeric products is going to be major, the other one is minor, and so we'll finish off this video looking at how to tell which one will be the major and which one will be the minor. Okay, so how do we predict the major product when we have different possible regiochemical outcomes? What we need to do is we need to consider the charge distributions. And to do that, we need to consider the resonance structures of both the diene and the dienophile. And so these are the same reactants that we had on the last slide. And so when we consider the resonance structures here, I have an allylic lone pair. So I can move the lone pair down, then the pi bond becomes a lone pair on this atom, giving me a partial positive charge on this oxygen atom and a partial negative charge on this carbon. On the dienophile, we've seen these resonance structures before with the electron withdrawing groups. So we can move the pi bond up to be a lone pair on the oxygen, creating a carbocation. We now have an allylic carbocation, so we can move that pi bond over. And so what we want to consider for the major and the minor products is, how do we compare the partial charges on the diene with the dienophile? And we want those to come together in a favorable fashion. And so we know that negative charges are attracted to positive charges. So what's going to want to happen in this Diels Alder reaction, in order to match up the partial positive on the dienophile with the partial negative on the diene, we're going to want to flip the dienophile around. And so we're going to want the electron withdrawing group pointing down relative to the methoxy group on the diene. And so that's what this slide represents. Right, we've taken the same reactants again that we've had on the last couple slides. We have the partial negative charge on the diene. We flipped the dienophile upside down so that it can interact with the partial negative charge on the diene. And so then this gives us the major product with the methoxy group on the diene being on, or farther away from, the electron withdrawing group on the dienophile. Now, this is not always the case, right? It's not always the case that they'll adopt this orientation. In every time you're given one of these, what you have to do is draw the resonance structure so you can figure out where are the partial positive negative charges to see how we want to line them up in the most optimal way in the product. All right, so I know I've given a lot of information on this Diels Alder reaction, and so the next video is going to look at some specific examples, similar to what will be on the homework and board problems, as well as the quiz and exams.